Alright, now let us debrief the mechanism questions from the worksheets. For the first question, you are given the structure of piperidine. You are asked to illustrate the mechanism from 12 to 5. Maybe at the beginning, right now at the first instance, you'll be wondering why are you given the structure of piperidine. So before we answer that, maybe we can look at the reaction scheme. So if you take a look at 12, which is over here, okay, and you take a look at 5, you realize that the bulk of the structure remains intact. The only part that is being changed is actually the aldehyde. So the aldehyde no longer exists. So if you want to look at it in a clearer fashion, let me just number the aldehydes. Number 1, and then carbon 2, and then it will be carbon 3. So this is carbon 1, and this is 2, and this is 3. So I think this will make it clearer. So you realize that the bulk of the structure remains intact, only the aldehyde has been changed. Okay, and you also realize one interesting phenomenon, that is this particular 6-membered ring, which is a diketones. 2 of it is actually being added in to the structure. So it's over here, and it's actually over here. Okay, and most importantly, let us look at the reagents and conditions. We have piperidine and we have ethanol. Usually ethanol serves as a solvent. You don't see any part of the ethanol being added, so obviously ethanol is a solvent. Then piperidine will be a key reagent, but what is the role of piperidine then? Okay, then we have to also ask ourselves the next question. What do you think is the mechanism from 12 to 5? Okay, so before we go into details, let's try to recall some of the mechanisms we have learned in H2. So the generic mechanism we learned in H2 are 5 types: nucleophilic substitution, nucleophilic addition, electrophilic substitution, and free radical substitution. Out of these 5 mechanisms, only free radical substitution is not ionic base. Not ionic base means it doesn't involve a nucleophile attacking an electrophile. Okay, so because if you take a look at electrophilic addition, the nucleophilic site is actually the pi bond. If you look at electrophilic substitution, the nucleophilic site is also the pi system in the aromatic ring. If you look at nucleophilic substitution, the electron-rich site is actually the nucleophile. Okay, so in this case, the lone pairs, either the lone pairs or nucleophilic sites will attack the electron deficient carbon that is bonded to the halogen. That's how nucleophilic substitution occurs. If you look at nucleophilic addition, again, is the nucleophilic sites, which can be a electron pair, attacking the electron deficient carbonyl-carbon. So normally, mechanisms they have learned involved is ionic based. Something that is rich, electron rich, minus, okay, attacking something that is deficient, which is plus. So minus attacking plus. Okay, so in our case here, you notice that the aldehyde group, which is 1, is kind of being attacked by the 2 diketones. And how can they be attacked when the diketone isn't even a nucleophile? Okay, so if this sets you thinking, then now you will realize the role of piperidine. The role of piperidine is actually to generate the nucleophile. How does it generate the nucleophile? Piperidine is actually a secondary amine, so it generates nucleophile by deprotonating a relevant hydrogen from the diketones. Okay, so now it makes it interesting already, because which proton is then acidic enough for the piperidine to deprotonate it? Okay, so now if we go back to the structure of the diketone, it looks like this. Okay, so if you recall from your H3, you learned that the hydrogen that is bonded to the carbon next to the carbonyl group is acidic. So we have HA here and HB here. So obviously HA is more acidic than HB. Why is that the case? Because it is flanked by 2 highly electron withdrawing carbonyl group. So the electron withdrawing carbonyl group will stabilize the conjugate base being formed via resonance. Okay, so this particular debrief is not about drawing resonance structures, etc. So I will leave that to you to go and figure out yourself. How come there are the resonance structures being drawn after deprotonating HA is more stable as compared to after deprotonating HB. Okay, so our main one now is really to try to illustrate the mechanism. So the first thing we need to show is your piperidine is actually a secondary unit. So remember that there is a lone pair of electrons on the nitrogen. So this lone pair of electrons will attack the hydrogens, and then it will push the electron density all the way to the carbon or oxygen. Okay, so in that case, we need to draw this out properly. Okay, so we get this, and then what do you think is next? Are we going to draw the whole structure of 12 out? Obviously not. So we are just going to represent it with a short form, which is represented with R. So in this case, I'll just draw it as an R group. Okay, bonded to the carbon. Okay, so remember that you need to draw in the lone pair. So the lone pairs of electrons over here. Okay, so is the oxygen attacks or the carbon? Obviously, the carbon is the one that joins, so we need to illustrate the mechanism by forming the pi bonds, and then this is the electron-rich pi bond that attacks the carbon here, and then nucleophilic addition occurs. Okay, so from here onwards, I think it's quite straightforward because the initial phase is basically to deprotonate HA to generate the nucleophile. This particular step is nucleophilic addition, which you guys should be very familiar with from H2. Okay, so after that, I'm going to just draw all the structures. Okay, this R here and O minus. Okay, then now after you get an O minus, what's going to happen? Are we going to continue to attack? So then, of course, now the next question will be a little bit harder because you're supposed to add in another of this group. This whole group is otherwise called the enolate. You're supposed to add in this group again, but you can't just add in like this, because if you just add like this, you cannot remove the O minus as O2 minus. So this is an impossible mechanism. Usually for beginning students of chemistry, especially in drawing mechanism, they will just whack and then kick the O2 minus out, but O2 minus is never observed. So you have to do something with regards to this particular intermediate for you to continue to draw the mechanism. Okay, so the most probable step now we are going to illustrate the mechanism is really to just to protonate the oxygen. Okay, because this actually makes perfect sense. How do we actually protonate the oxygen? Okay, remember that earlier on, right? This particular base, piperidine, it generates the conjugate acid. Okay, so obviously now making use of a conjugate acid makes perfect sense. Okay, so the lone pairs will then attack the H, and then you generate back the piperidine. Okay, so I'll just draw this below. Okay, I'll just draw this below like this. Okay, and then I get the OH here. Okay, after generating the OH, you'll be wondering, so what is next? Okay, what is next is actually quite crucial, because the question you might want to ask would be, again back to the same question, do I use the enolate, right? Do I actually use this particular enolate that I used previously? Okay, just erase this for now. Do I use this particular enolate to actually whack this carbon and to kick out the OH minus? Most people will actually do something like this. To be honest, for H3 level, if you do something like this, we can't exactly fault you entirely, because you are not equipped with the knowledge to actually make a slightly more informed guess on what exactly might happen. Okay, but the truth is the actual mechanism doesn't work the way it does, because this will actually involve a pretty high activation barrier. So how does it work? Let me just illustrate to you here. not too not too difficult to actually guess or understand. Okay, remember that we have another acidic proton, and then we have our pyridine right now. It can also deprotonate this again, right? Because it's definitely acidic as well. Okay, so we are performing the same thing. Okay, and then in the process, we're going to draw out the innovate again. Okay, what's going to happen here is a mechanism that you don't learn in H3. It's called first order elimination conjugate base, or otherwise called E1CB. Okay, so for this E1CB, you're going to generate an alkene that looks like this. And for this particular alkene, there's something interesting because delta minus delta plus delta minus delta plus. So this particular alkene is actually, there is actually a hidden electron deficient site at the end of the alkene. And because of this, it allows the conjugate base of this particular enolate to actually attack it. And yes, you can continue to draw, and this is exactly how 12 is being formed. Okay, I will not continue to draw for you, but I'll just show you directly from the chem draw. Yep, essentially I've drawn almost everything for you. So this is the first order, this is the E1CB that I talked about earlier on, and then the protonation and deprotonation, and then the final bit would be to actually generate 5. Okay, so essentially this is the mechanism from 12 to 5. Okay, so as a summary, right, you realize that the little bit of additional information you have learned in H3 can actually help you to understand a lot about reaction mechanism. Okay, the only difference is that you need to combine the dots. You need to connect the dots and make meaningful sense out of it. Okay, so of course the first thing is how to generate a nucleophile from the diketones, and then how do you perform a simple or rather nucleophilic addition from the nucleophile being generated, and then how do you draw a proper protonation step later on. The E1CB part, I would say, is a little bit beyond most of you, but still it doesn't really matter because you can still draw it. You can still draw the one that attacks the OH, attacks the carbon and then kick out the OH minus, although it's not as favorable. Okay, but experimentally it has been shown that in alkaline medium the E1CB is actually favored. Okay, right. Okay, now let us go back to the next question. Okay, for question 2, you are told that PPTS is a source of protons. You are asked to illustrate the mechanism from 12 to 11, given the confirmation of 15 shown below. Since you are given the confirmation, I hope you can sort of guess that when you are illustrating the mechanism, you're supposed to keep the confirmation in place. It's actually to help you in the mechanism as well. So let us take a look at the research paper. So from 15 to 11, it seems a bit complicated, but if we are to label the carbon, then it will be a lot easier. So let me just number this as 1, 2, and 3, and 4 over here. Okay, so if you take a look at this particular numbering, I hope it does help a bit. So this is carbon number 3 and carbon number 4. Okay, so now I hope it makes perfect sense how they are being joined and how to actually illustrate the mechanism. We'll go back to the um, blank documents. Okay, so I've already drawn something like this earlier on. It's actually to make the illustration easier. Okay, first of all, right, you'll be asking what is the purpose of having the protons. Okay, I can tell you straight that most of you might draw something like this. Basically, just the lone pair attacking the carbon and then generate the alkoxide as though you are drawing a nucleophilic addition from your H2. Okay, remember in your H2, a very basic nucleophilic addition mechanism you need to draw is the addition of HCN onto, say, a ketone or aldehyde. But I have to say that if you draw something like that, then it will be kind of a mistake. Okay, the reason is number one, alcohol is not a good nucleophile. So if you are expecting the oxygen to attack the carbonyl-carbon and to generate the alkoxide, it will going to take a very long time. Okay, so number one, alcohol is not a good nucleophile. Number two, the alkoxide intermediate is not stable. And in an acidic medium, you are not going to expect the alkoxide to be formed because you can't have an O minus, which is alkoxide, in an acidic medium. So with this in mind, you want to lower the activation barrier. How do we lower the activation barrier? By having the acid, which is H+. So in this case, for most of nucleophilic addition involving ketones and aldehydes in an acidic medium, we will normally protonate the carbonyl oxygen first. Because in the process of protonating the carbonyl oxygen, you are actually generating the conjugate acid of the ketones, and it makes the carbonyl-carbon more electron deficient because having a plus charge at the oxygen when it's protonated, right, will cause the OH plus to be a stronger electron withdrawing group, and the electron withdrawing nature will make the carbonyl-carbon more electron deficient. Okay, so with this idea in mind, I'm just going to erase this. You would expect the H to be protonated, and in the process, the lone pairs of oxygen will then perform a nucleophilic effect on the carbonyl-carbon, and then the carbon will shift. Okay, so I hope when you take a look at this, then you will be able to understand or to draw to actually draw the first product out, the intermediate product. So you can look at something like this. Okay, and then there's an OH here, and then an O, oops, and then an O here, then the other OH, and then the R, and then this O, of course, is protonated as well. Okay, so with this into the picture, you're going to expect intramolecular proton transfer, okay, between the alcohol and this ether oxygen. Okay, and in the process, let me just redraw this again. I'm going to have something like this, and OH2 will be a good leaving group. Okay, and then you expect the lone pair to come in again to reform the carbonyl group, and then you kick up the H2O. Okay, then once you reform the carbonyl group, the rest of the chemistry will happen because you have a plus charge again in the carbonyl group, and then the alcohol will then perform another nucleophilic attack, and then the carbon will break. Okay, and then later on it will deprotonate. Okay, so I hope with this particular illustration you will see a few important points. So let me go to ChemDraw so that it's clearer for you. Okay, so again, the first step involved the protonation of the carbonyl oxygen, and then to make the carbonyl-carbon more electron deficient, and then the alcohol will then perform a nucleophilic attack. You'll be wondering, is this alcohol better or the other alcohol better? For H3 wise, because there are some specific things you have not learned, actually either one works. Okay, so in this case, I just use the one below to attack it first, and then intramolecular proton transfer, and then the H2O will leave, you reform the carbonyl group, and then you perform another nucleophilic attack, and then the rest will take place. One of the mistakes that most students will make over here is, instead of forming the carbonyl group, the student will simply use the lone pair on the alcohol to whack this carbon to kick out the H2O. But if you realize but if you draw it in this particular fashion, it is not possible, because for the lone pairs on the alcohol to whack this carbon, right, it will be SN2 like. For it to be SN2 like, it has to come from the rear, but the rear is an impossible part for the OH to approach. So in that case, a nucleophilic light addition mechanism works a lot better. Okay, so I hope you take this lesson in mind, and in all the future mechanism you draw involving such system, you do not use the nucleophile to directly kick out the leaving group. Okay, now let us take a look at the last parts. Okay, I think the question 3, I don't need to explain too much to you, because for question 3 you are given the intermediates 16. So let me just zoom in a little bit. Okay, so you realize that this thing actually opens up. So with the earlier idea in mind, I hope you can actually see that your first step should involve the protonation of this particular oxygen. Okay, sorry, it's a bit thick. Okay, the protonation of this particular oxygen, and then in the process, the lone pairs on the lone pairs on this group. Sorry, just the lone pairs on this group will just come in and it will kick out this oxygen, and this is how you form 16. Okay, right? And after you have formed 16, how do we ensure that we are going to reach 13? Okay, so you realize that there is a hidden electron source here. So this hidden electron source, the lone pair will just come in like this. That is how this particular part is being formed, this particular portion. Okay, right? So with this illustration, I hope you are able to see how this particular portion can be formed. And then maybe the final bit, I won't really go into details, will be the alcohol here. Of course, will then perform a nucleophilic attack on this carbonyl carbon, but of course it doesn't attack directly in a way that you are told. Okay, so there must be some form of protonation that will take place. And then after that, you will reform the enolate. Okay, so just go straight into ChemDraw so that you can see directly what exactly is happening. Yep, so basically this is the part that I was illustrating to you, and of course I didn't illustrate to you the water attacking this carbonyl carbon parts, but we don't need to go into such details earlier on, because these are some of the details that you should be able to figure out yourself. Okay, then after that, the last part is basically just protonating the oxygen, and then the alcohol will act as the nucleophile to attack the carbonyl carbon. Okay, so I hope with this particular illustration you will be able to be a bit clearer about the objective of learning H3 is not just to pass exams, but also given a research paper of this kind of nature where it involves several forms of protonation, deprotonation, addition, elimination kind of mechanism, you should be able to make some sense of it, and then to illustrate the mechanism as it is. But of course, illustrating mechanism is just one aspect of H3. But at the end of the day, to appreciate literature, to appreciate how the research work are being done, I think is more important than anything else. Yeah, so I hope these two series of workshops or lectures, you want to call it, helps you to better appreciate how researchers perform their research, and how you can read through a research paper confidently on your own. You need not understand every single thing, but at least you'll be able to understand the bulk of what they are really trying to do. Okay, so with this, we'll see you the next time around.